All right. So welcome to the virtual Marine Seismology Symposium. My name is Casey Adderholt and my pronouns are she, her, and I am an earthquake seismologist working at Incorporated Research Institutions for Seismology, currently at the headquarters in Washington, DC. Our nation's capital is located on the ancestral lands of the Anacostans, with this land and surrounding regions being stewarded and cared for by the Cedarville Band and Wild Turkey Clan of the Piscataway Conoy Nation, the Piscataway Conoy Tribe, and the Piscataway Indian Nation. I come from Homer, Alaska, where the Dena'ina people have been in community long before the occupation of settler culture, past and present. As a visitor on these lands and waters, I strive to deepen my own understanding of the local indigenous communities in the regions I reside and work in. I come with respect for this land that I'm on today. I invite each of you to also acknowledge and reflect on the indigenous people who have and do reside on these lands where you are coming from, and who have navigated these waters where we carry out our scientific investigations. I'd like to start us off with a few announcements before handing this over to the session conveners. Please note that all attendees are expected to adhere to the IRIS meeting code of conduct. If you are the target or witness any unacceptable behavior during this symposium, whether verbal or in text, please notify an IRIS staff member, symposium organizer, or get in touch with IRIS Business Operations and HR Manager, Marlo Swanson. By this time, you've been able to navigate successfully through the meeting agenda. Please note that while main sessions and live poster sessions are automatically added to your agenda, you should add any special interest group meetings that you would like to attend. The High Resolution Small Source Seismic Special Interest Group has an open survey to collect responses that will spark discussion during the meeting. The first part of the Broadband OBS Data Processing Special Interest Group meeting will be open to all. However, the tutorial portion will require prior sign-up. And I will also post that sign-up form in the chat in a minute. Our other special interest group meetings include Justice, Equity, Diversity, and Inclusion, where we will share ideas, resources, and strategies. The Frontiers in Marine Electromagnetics, with science talks and community discussion, as well as a final strategy session on SC4D. Final being the final day of our conference, not the final time that we'll talk about SC4D. Live poster sessions are scheduled both weeks, and we encourage all participants to view the longer recorded videos and PDF materials for posters, especially those in the open session that does not have a live component. I will now hand this over to Marine Seismology Symposium Organizing Committee members, Monica Kohler from Caltech and Sean Higgins from Lamont Doherty Earth Observatory, to introduce the speakers in this session. Sean?
Casey, if you forward one slide in your presentation there to the agenda. I don't know if you show the agenda, maybe it's slide 3.
Right here.
There we go. Yeah, so Monica and I would like to welcome everybody. I appreciate all the help from Casey and her team and stuff in coming together for this presentations today. I've known Donna Shillington for a long time, and I've been working with Emily Roland on a current planning cruise right now. So I've gotten a chance to know them both a little bit. The first speaker tonight is Dr. Emily Roland. She's currently assistant professor at the University of Western Washington University. Recently moved there from the School of Oceanography, where she was assistant professor at the University of Washington. So she comes by way of her PhD in marine geophysics at the Massachusetts Institute of Technology Woods Hole program. And with that, I will let her go into her talk, and we'll introduce Donna a little later.
Great, thank you so much, Sean, for that introduction. I'm gonna share my screen here. Hopefully this works, and if it doesn't, please somebody tell me, because I can't necessarily see what you see, but I'm not getting any thumbs down. So I'll assume you can see my opening screen here, and I'm gonna, but before I get started, I'd like to thank Monica and Sean and Lindsay for organizing this opening session. And I'd also like to, I'm gonna kind of butt in here, and I'd also like to take the opportunity to thank Casey Adderholt. And I'm going to take a little bit of my 30 minutes here to just say that I think Casey's really shown amazing persistence and determination through the last actually more than year of planning and then challenges that we've confronted. And I'm going to do something, or try to do something, that may not work, but before I go on here with my science talk, I actually was just going to ask if everyone would turn on their videos for 1 minute, if you're comfortable doing that, and unmute yourself, and give Casey a quick round of applause for all of the planning work she's done in bringing this community together amidst the last year. So,
Woo! All right. Thank you.
Right.
Thank you so much.
Thank you, everybody. Yeah. And yeah, Casey, I just want to say that, I think as marine seismologists, we're all used to working in remote settings to some degree, but this year has provided us with a new perspective on the challenges of remote work. And for me, it has made me almost wish that I was out on a boat in the middle of the Pacific so that I could connect with my community. And so this meeting, I think, will be a great opportunity for us to do that, even if we're doing it from all of our home offices spread out across the country and the world. So thanks again, Casey. Okay, and with that, on that note, I'm happy to have the chance to share with you a talk that I think will be an introduction to several experiments I'm involved in, along with many, many collaborators that I'll be hopefully referring to throughout the next 20 or 30 minutes. And all of this work generally falls under the umbrella of having a focus on faulting and active deformation. And so here there's some photos that I've borrowed and stolen from various folks who've been out to sea collecting seismic data associated with these 4 experiments throughout the last several years. But to kind of try to link everything together before I get going, I just wanted to sort of touch on what I see as some of the overarching questions that we're maybe as a community still trying to think about with regards to slip behavior, material properties, and structure of big plate boundary faults and faults that might host significant geohazards. So in the way that I think about these things, and I think science questions that I'm hoping will be somewhat of a consistent theme throughout these experiments I'm going to go really quickly through, are kind of thought about in 2 ways. From one perspective, these projects are focused on thinking about what the detailed rheological conditions that influence seismic and aseismic slip in 4 dimensions, in space and in time, along active plate boundary faults. So those of us who think about plate boundary fault slip and fault slip on big active faults are often really concerned with when and where fluids play a significant role in fault slip behavior, and how do we use tools and observations and geological insight to identify the relevant physical properties. Okay, so that's sort of one of the things that we're hoping to get after, myself, and I know many of you who think about earthquakes and plate boundary fault slip behavior. Another perspective that kind of a different way of thinking about this is from more of a kind of structural perspective, and thinking about how do patterns of deformation kind of along and surrounding active faults illuminate their past and future earthquake behavior. And so with this, I'm thinking about things like, what does a damage zone look like along a particular segment of a fault? Or what are the kind of fine scale or coarse scale geometrical constraints or associated secondary features like splay faults or fault branches that might tell us something about the kind of fault slip behavior we should expect in the future. And so I really don't have time for this, but I'm going to try to touch on 4 different experiments that kind of span the western or the eastern Pacific here, starting all the way down with the Ocean Ridge Transform Fault and ending kind of up in Alaska. And almost all of these projects I'm going to start by mentioning are works in progress. And so I won't be actually presenting too many results from these various experiments, but I'm hoping you can see this talk as kind of an advertisement for science to tune into, some of which is actually going to be presented. Results will be presented at this meeting from different people, but also, maybe you can look for in future meetings, marine seismic symposiums that will hopefully happen in person, in the next year or so. Okay, and so to dive right in, this is when we think about these questions of fault zone, thinking about fault zone material properties and rheology and how they influence earthquake rupture behavior, arguably one of the best places to think about those questions is at mid-ocean ridge transform faults, like the one I'm showing you up in the upper right portion of your screen here. This is kind of a zoom in of the bathymetry surrounding the Quebrada Discovery Gofar fault system that's offsetting the East Pacific rise just south of the equator. Here it is in kind of map. And so if you feel like, if you're new to oceanic transform faults and you question my comment about this being one of the best places to think about fault mechanics, I will admit that this is where I did my PhD work, starting probably more than 10 years ago, well, more than 10 years ago now. So I might be a little bit biased, but there are some features of oceanic transform faults that I think do make them very unique and advantageous for kind of using as natural laboratories. And so I won't talk about all of them now, but a couple of those things that might make these fault zones particularly good for studying the controls on earthquake fault zip have to do with the fact that they're very high slip rate faults, 14 centimeters a year for the QDG system. They occur in young, hot, probably pretty weak, and what we think of as being fairly uniform oceanic lithosphere. However, there's also some things about these transfer fault systems that are surprising. And here's a picture at the very bottom of your screen of Margaret Betcher and Jeff McGuire. And again, many years ago, one of these surprising features of transform faults that Margaret and Jeff started to notice were that they exhibit sort of on an average sense a low overall seismic coupling. And so when you look at the earthquakes from using sort of teleseismic data that are sourced on oceanic transform faults, they don't represent enough of the seismic moment release that we would expect based on, you know, strain rates along these faults. And so we think that some significant portion of the slip on transform faults has got to be occurring without generating these large earthquakes. And so sort of one of the motivating questions behind a lot of work focused on transform faults is how is that slip actually being accommodated, and what are the mechanisms that sustain both the, you know, fast seismic ruptures that we see in magnitude 5 and 6 earthquakes on this QDG fault system versus what's happening sort of with the rest of the strain along these faults. Okay, and so, whoops, I'm going to go back here. And so I'm just going to kind of walk you through this figure on the left in case you haven't seen this before. And so in addition to observing this overall low seismic coupling on the QDG and kind of other transform faults globally, one of the things that this kind of represented by this plot that Margaret makes and is continually updating that was also observed is that these faults have a quite regular and predictable earthquake cycle that's short in duration, making it convenient for studying with ocean bottom seismic observations, and sustains, you know, larger earthquakes on what appear to be overlapping rupture segments. Okay, and so with the colors on this plot, this is time. So you'll see that like the red dots on the westernmost segment of Gofar happen about every 5 years. And what the colors indicated by in this plot are sort of estimates on overlapping areas that sort of sustain these repeat magnitude 5 and 6 earthquakes. And so this was sort of the first hint that there may be important sort of along strike variability in the mechanical behavior of these transform faults that prompted the first generation of sort of detailed seismic investigations to be coordinated in 2008. And before I move on to the next slide, I'll just point you towards these black boxes on this figure. So remember, this is sort of time and longitude along the fault system here. And the black boxes indicate ocean bottom seismic instrument deployments that have been coordinated now during kind of 2 different periods separated by almost, you know, by 10 years in between. Okay, and so if you'll remember from that previous plot, there was kind of excitingly one of these red dots that occurred right in the middle of one of these seafloor OBS deployments on the Gofar fault in 2008. And I'm with this complicated slide, I'm going to kind of try to walk you through some of the observations really quickly that were made that have kind of motivated the next generation of questions to be asked about how kind of fault slip behavior is accommodated oceanic transform faults. And so in the upper left here is a figure summarizing some of the earthquake behavior, particularly during the end of the seismic cycle at the westernmost segment of the Gofar fault. And so first of all, the thing to maybe recognize first is that the magnitude 6 earthquake that was represented by that red dot on the previous slide ruptured a portion of this segment that is kind of highlighted by the aftershocks and these red little aftershocks that popped off along the fault. Here's the focal mechanism, strike slip focal mechanism, that large event. But adjacent to the sort of main shock rupture area, this is now a depth slice, preceding the earthquake, there was a significant swarm of small magnitude events during a period of really elevated seismicity rate that that sort of was distinctive both in terms of the elevated, the high seismicity rates confined to a segment of the fault, a kind of a 10-kilometer wide segment of the fault adjacent to what ended up being the main shock rupture extent, that demonstrated some really unique properties in terms of this kind of space-time evolution and even the material properties of that, what we think that kind of foreshock swarm zone was characterized by. And so again, I could spend like an hour talking about this, and I have to be really careful not to. But in a nutshell, if we look at the depth distribution of earthquakes, we get maybe the first hint that there's something really distinctive happening when kind of a long strike at the Gofar fault. We see that this foreshock swarm extends to greater depths by maybe a factor of 2 as compared to the aftershock kind of main shock region. This figure in the bottom right here also shows evidence of actually time-dependent changes in elastic properties within this foreshock, kind of this foreshock zone that were observed based on waveforms of these small magnitude earthquakes that popped off in the foreshock zone area. And so what this is showing in sort of the black dots on the left here is an estimate of the S-wave velocity, sort of a subtle evolution in the S-wave velocity during the foreshock sequence that indicates that based on the sort of coda of these S-waves, there was a decrease in the S-wave velocity of 3% or so sort of during this foreshock sequence. So this is telling us there's something interesting going on during this foreshock sequence. There's potentially some kind of evolving stress states within this zone, and that it's again, it seems to be distinct from sort of the properties within maybe one of these like more predictable or more normal aftershock regions. The last thing I'll mention is that we also had an active source component of this experiment, and a wide angle refraction data set was collected in what turned out to be the foreshock region. This is shown by the white line here. And this is a arrival time tomography model. This is kind of the P-wave velocity crossing this foreshock region. And what it shows is that there's a significant damage zone associated with this foreshock sequence that extends well through the crust. Less well resolved into the upper mantle, but possibly into the upper mantle. That's probably telling us that there's either a big wide damage zone characterized by increased porosity, or potentially a combination of porosity and altered materials that are present here. Okay, and so those are a lot of results, but it's allowed us to sort of start to probe into the next level of complexity with regard to thinking about, what is it that really makes this sort of what we might maybe now call a rupture barrier zone distinctive from a part of the fault that can sustain regular big earthquakes, okay? And so this is comparing that yellow zone to the red zone, and what is it about the material properties that make that unique, and what are the slip mechanisms that occur in those two distinctive segments of the Oceanic transform fault setting. And so there's sort of a even more diverse team of people who are coordinating the next generation of marine seismic and actually sort of marine geological investigations across the Gofar fault right now. And I'm not going to give this the time it deserves. I just kind of want to advertise as this is happening. John Collins, who's here, he's in one of these pictures, has actually just gotten off cruise leg 2 of 3, in which he recovered and redeployed a kind of complex array of broadband, short period, and actually seafloor strong motion accelerometers across multiple segments of the Gofar fault shown here. And this kind of 10 years later, this renewed suite of science goals is really targeting through a combination of different observational strategies, what is it that's responsible for this variability in mechanical properties and potentially slip mechanisms along oceanic transform faults. And so, can we, for example, think about these rupture barrier zones as being characterized by unusual geology, maybe a melange of velocity strengthening and velocity weakening material that's allowing for, some small scale earthquakes, but potentially other types of slip, aseismic slip in those zones? Or is there maybe a different explanation that invokes something like strong dilatancy strengthening, so a kind of more sophisticated rheology model that might be a better explanation for some of the observations we've made at Gofar? And so to do this, we're not just relying on fancy marine seismic observations, although we're trying to do that as well. So here's Wenyan Fen, who's working actively at kind of coordinating 4D characterization of the elastic properties of the seismic velocity structure within this foreshock zone using these mini arrays of short period instruments that are shown here, kind of zoomed in along this, this portion of the westernmost segment of Gofar. He's going to be using sort of a double beam forming method that I'll let Wenyan describe to you in more detail later in the meeting, if he has time, but to sort of monitor the velocity structure of this portion of the fault kind of throughout the seismic cycle during this 2-year deployment. But in addition to the seismic characterization, there's kind of a big dredging effort that's been coordinated by Jessica Warren, where she's collecting fault zone rocks and looking for evidence of the types of geological properties that might help to explain some of the observations we've made about variable types of slip behavior. On the final leg of the cruise, planned for about a year from now, the AUV Sentry is also going to be coordinated to collect a microbathymetry side scan, water column, and sort of sub-bottom data set, doing really fine scale kind of geologic mapping of the shallow subsurface and seafloor surrounding these segments, and looking for evidence of maybe enhanced hydrothermal circulation or other variable sort of geologic and hydrogeologic features along the fault zone. Okay, and so this is just to finish this little portion of the talk. This is bathymetry data that was just collected from this leg 2 survey. Somehow John Collins managed to do this amidst all of the other things he was doing with a miniature science party on this cruise. But this kind of shows you what this kind of main shock zone and rupture barrier or foreshock swarm zone looks like. And so, I think it's just indicative of how we have a really evolving view of what these, fast slip rate ridge transform faults look like, that's changing from this simplified picture we had maybe when we went into this question decades ago, and thinking about them as actually pretty complex structures with complicated, geometrical characteristics and certainly rheological and fault slip behavior. So watch for more information on that. Okay, so quickly here, I'm also just going to kind of highlight some work going on in Cascadia. So I'm moving north now to the margin of North America and the Juan de Fuca Plate on the edge of the Pacific Ocean. And I'm going to just sort of touch on using a different type of data with different resolution to start to think about, how can we, again, characterize kind of the, in this case, the forearc of a subduction zone setting, to think about how sort of in more detail, the offshore portion of this, of the Cascadia subduction zone might be evolving through time, and potentially how we can learn about the plate boundary itself by looking at the forearc. And so this is work that's being coordinated in collaboration and really being coordinated by the USGS Coastal and Marine Group. Here's Nathan Miller and Janet Watt. And some of the sort of initial images I'll show from this high resolution marine seismic reflection data set are being worked on by a student I work with at University of Washington, Emma Myers. There she is setting off an XVT, I think on the Langseth with a big smile on her face. But but what the plot on the left shows is a really significant data set that was collected, I think in 2018 and 19, all along the Oregon and Washington margin. And so what the pink lines here are showing you are high-res MCS profiles crossing sort of the outer wedge of the Cascadia Forearc here, Cascadia accretionary prism. And so as you can imagine, this data set, it's new and it's of a little bit of a different variety than other seismic reflection images we've had to work with in the past. And I think it's going to both complement some of that legacy data as well as some of the upcoming data that we're anticipating for the Cascadia margin in the next couple of years. Here's the Rachel Carson, a UW kind of regional class vessel decked out with a whole bunch of seismic gear that was used for this data acquisition effort. And what Emma in particular is thinking about is how she can use sort of some of these higher resolution images from this Sparker and high-res streamer configuration to try to link shallow structural features with what we think we know about sort of the crustal scale forearc margin. And so the red lines here show the coast survey from 2012. And now I'll jump right to kind of a comparison of what this data looks like. And so I'm just showing you a quick example of this. This is the coast. This is an interpretation of one of the coast profiles from Susanna Webb's thesis in 2017. She's a student working with Harold Tobin. And you can see these really kind of beautiful, landward vergent imbricate thrust structures that's kind of allowing for the evolution of the forearc and some of the seafloor morphology features we see along the Cascadia margin. Some of these faults are connected with the plate boundary, we think, some of them may not be. And in a zoomed in version of the high-res data that Emma's been working on from this kind of collaboration with the USGS, she can kind of see in much more detail what this faulting structure within some of these kind of smaller scale forearc basins look like, and start to even think about how both faulting and folding provides insight into the time and sort of spatial evolution of the accretionary, or the outer wedge of the accretionary prism, and also think about, what she might be able to tease out about the connectivity of the shallow structure and the longevity of certain fault features with respect to activity that we think is happening along the primary plate boundary fault. So I'm not going into nearly enough detail here. These are just a few kind of initial interpretation structures that she's been piecing together as she examines these accretionary wedge basins. There's a BSR and maybe even a double BSR that extends through there, and significant folding in the shallowest portion of the basin structure. But this is another project that's sort of ongoing and focused on thinking about how sort of the geometry and structure of the forearc can tell us something about the evolution of the plate boundary fault zone. So I'm probably quickly running through my time here, but for the last sort of couple minutes here, I want to just advertise a couple more projects that moving north along kind of now the boundary between North America and the Pacific plate. And so here I'm showing you now the Queen Charlotte fault. So this is north of Cascadia. You have to cross the Queen Charlotte fault if you're going to move from the Cascadia subduction zone to the Alaska Aleutian subduction zone. And so, considering that the Queen Charlotte fault is capable of generating really large earthquakes and sustains significant slip rates over 5 centimeters a year, definitely on par with the San Andreas system. Until relatively recently, the Queen Charlotte fault, I would sort of say, has gotten relatively little attention. Many people compare it to the Southern San Andreas, but there's many primary questions that we don't understand very well about the Queen Charlotte. For example, and probably the most major one of those relates to the fact that we know that the Queen Charlotte has a systematic change in the sort of degree of obliquity or the degree of convergence moving from south to north. And so here, this plot in the upper right shows sort of marching along with latitude from south to north along the Queen Charlotte. Here's a distribution of magnitude 7 and 8 earthquakes that have happened along the fault throughout the last 100 years. And then, the evolution of sort of how much transpression we expect along the fault, moving in the south with a relatively high degree of transpression, to in the north something much closer to kind of a pure strike system. And so, looking at some of the primary features of the Queen Charlotte Way in this way, and thinking about how this change in obliquity, as well as a systematic change in the Pacific plate age, might influence sort of how faulting and earthquake behavior occurs along the fault, we can start to ask some questions about what we can learn about fault kind of slip mechanisms and structural evolution along the Queen Charlotte. Here are just some examples of sort of seafloor morphology that we see as we compare the southern, central, and northern portions of the fault. In the south, showing a well-defined terrace, potentially indicative of crustal shortening, or potentially even a miniature accretionary prism. There's some debate about whether underthrusting happens in the far south. In the central segment, characterized by a complex pattern of ridges and sort of deformed basins oblique to the margin, and in the north, this really linear kind of localized fault zone, more similar to sort of a primary vertical strike slick system. And so we think this has to do with the sort of orientation of the stress field and the primary stresses evolving from south to north along the Queen Charlotte fault. Okay, and so I mentioned that, recently this fault has gotten a little bit more attention, in part, I think, because it's sustained some really surprising earthquakes in the last sort of decade. And so here on the left, as a part of this map, you'll see the aftershock zones from the 2012 magnitude 7.8 Haida Gwaii earthquake, which was primarily a thrust event. Just a few months later, and a few hundred kilometers to the north, the 2013 magnitude 7.5 Craig, Alaska earthquake was a strike slip event. And I think these earthquakes brought the fault to our attention and made us start to look more closely and think about, okay, how does this evolving obliquity manifest itself in the fault structure, and what can we learn about the details of the fault zone and the material, sort of how the Pacific and North America plates evolve from south to north. And so the USGS Coastal Marine Group has in the last several years has engaged in a really in-depth mapping effort to try to think about sort of how does this fault behave and what can we see in terms of surface morphology. And so here's Danny Brothers and Nathan Miller, who have been collecting a lot of high resolution sub-bottom and seafloor bathymetry along the entire Queen Charlotte Fault. And what they find is that the Queen Charlotte cuts the seafloor along a really surprisingly narrow and straight trace, which has allowed them to determine some detailed slip rates and geometrical mapping along the extent of the Queen Charlotte. And so here on the right, you can see, this is again a bit of a complicated figure, but you can see that there's actually, you can estimate kind of micro variations in the fault geometry that allow you to kind of estimate small regions of actually divergence or convergence as you work from the highly convergent south up into the north, which they've correlated with earthquake behavior. In this plot, in the upper portion of your screen is kind of a glimpse at the seismic velocity contrast across the fault in the area of the Craig earthquake from Marine Walton aftershock study from the Craig event. And what we see is kind of a surprising contrast where the North America plate actually seems to be a little bit slower than the Pacific plate actually appears to be a little bit slower than the North America plate, which is maybe different than what you would expect for kind of oceanic crustal depths. And so it kind of just highlights the fact that we can begin to start to ask some more sophisticated questions about the evolution of the Queen Charlotte Fault from north to south. Okay, and so in the interest of time, I'm not gonna read all of the text on this slide, but all of this work has prompted a detailed crustal scale, active, passive investigation of the Queen Charlotte Fault that's been planned first starting this year, or starting last summer, and then kind of delayed until this summer. And you're seeing the experiment plan for the Queen Charlotte Fault experiment on the left here. And so, yellow lines are wide angle refraction lines planned using the Langseth. Green lines are, this is actually an older version of this figure, but are multi-channel seismic reflection profiles. And then there's 2 to 3 arrays of broadband ocean bottom seismometers that have been planned to kind of explore earthquake behavior and seismogenesis along the fault. And so this effort is being coordinated by the LEPI, Lindsay Worthington, Maureen Walton, and Mladen Edmorovic, and as well as myself. But with a really big collaborative group from the USGS Coastal Marine Group and the Natural Resources Canada and the University of Victoria. And so again, this project is really exciting. It's large scale. It's gone through evolution of challenges throughout trying to be coordinated during a global pandemic. Here you see, this is Lindsay planning line locations, I think in 2019, which evolved to, me waiting in line for a COVID test prior to going into quarantine, trying to get on board a ship last summer, which unfortunately was canceled and delayed till the summer. And so there have definitely been a few, obstacles associated with following through with this experiment. But I also kind of think it's worth reporting a lot of positive kind of features of this experiment also. So what you're looking at here are the 2 vessels that will be coordinated. The active source, here's the Langseth, and the OBS support ship. This is the Canadian Coast Guard vessel, the John P. Tully. And so this is really just indicative of the international collaboration that's being coordinated as part of this large scale study, crossing the US and Canadian border. Additionally, and this is kind of fun, that I'm sort of honored to be able to report that I think the Queen Charlotte experiment will be one of the first applications of a new Canadian OBS facility. And so this is an example of one of the new Aquarius broadband OBSs that are being planned for this large scale, the Canadian National Facility for Seismic Imaging, NSFI, as Mladen tells me. And these instruments are actually kind of planned and will be coming available in the next couple of months. And I believe that the southernmost passive source array is going to be coordinated with these Canadian instruments in the next year. So that's really exciting. And there's been other facility updates throughout the duration of this experiment that I think are all positive updates to our community. Okay, so I don't know how much time I have left, but probably not very much. And I just wanted to kind of finish with a quick Thank you, Casey. I finish with a quick kind of update, and again, kind of an advertisement for some of the exciting kind of data and starting to be results that have come out from the AACSE, the Alaska Amphibious Community Seismic Experiment. And I was emailing with Grace Barczyk recently, kind of in preparation for this meeting, and I was sort of saying how excited I am to be able to be presenting some science results from the AACSE soon. And I'm not really going to be doing that here in 5 minutes, but I think at this meeting, if you keep your eyes out, you will definitely be seeing some examples of really exciting research that's being done with the AACSE. And so I can't imagine you haven't heard of this already, but just in case you haven't, this map on the left illustrates kind of the extent of this unprecedented broadband seismic deployment across the Alaska Peninsula. So the colors here indicate all kinds of different kind of flavors of broadband ocean bottom seismometers that were deployed across the margin for 18 months-ish, or at least that was kind of the goal of the experiment, as well as kind of a densification of the land arrays that exist along the Alaska Peninsula and on Kodiak Island. And so this experiment was designed to address a broad array of science goals that span everything from imaging the Pacific plate and the North America Forearc to kind of trying to characterize Megathrust plate boundary characteristics, looking at earthquake source properties. But the broadband experiment ended up being complemented by a lot of additional components. And so here, for example, is a map showing a dense nodal array that was deployed. This was coordinated by Lindsay Worthington and others along kind of the eastern coast of Kodiak Island. And so you can imagine that this really expands the type of observations that are made along sort of a transect of this portion of the subduction zone. On the right here, these are figures that you can find in SRL paper by Barczyk et al. And from last year, they kind of highlight the amount of data that was and the quality of the data that was produced from the AACSE. This is an image from some of the shipboard sort of underway data that was collected during the 5 cruises that contributed to the sort of logistics of this experiment. So here's multi-beam bathymetry data and sub-bottom profile data from the Langseth that covers a portion of the 2018 magnitude 7.9, I believe, Pacific plate event offshore Kodiak. And so there's all kinds of science questions to be asked just about this event that the AACSE wasn't even designed to address, but this is just kind of an example of the diversity in data. Quickly here, I'm not showing any examples of the actual data, but this illustrates the kind of an active source component as well. So the Langseth shot over several transects kind of spanning the Samiti segment of the Alaska Peninsula through the Kodiak segment here. And so, this will also kind of broaden the amount of the amount of imaging methods that we might be capable of engaging in using this data set. There was also, I think, some kind of shorter streamer MCS data collected along these transects. So, and I won't go into detail with this, but it should be mentioned that the AACSE also incorporated a pretty significant component of education and outreach activities. And so Abrea Adams at this meeting, I believe, will be kind of going into greater depth about what some of these activities included, but I think this was a really important component of this experiment and will continue to be an important component of all of the things we do with marine seismology. And so this picture is from an undergraduate workshop on Kodiak Island, but tune into Abrea's talk for all of the details on that. And so again, just kind of the last slide or two here. This is just a couple data grabs from the AACSE broadband instruments. So my group in particular, we're sort of interested in thinking about earthquake source properties across the margin and how we can learn about how strain is being accommodated along different kind of a transition portion of the Alaska subduction zone, where we think we have sort of relatively low seismic coupling in the Samiti segment to relatively high coupling in the Kodiak and the Shumagan segment, high coupling in the Samiti and Kodiak segments. And so it's exciting to be able to think about actually having high quality seismic recordings of even small scale earthquakes spanning full azimuthal range and capable of making really high quality observations of P waves and S waves across the margin. So again, this is just like a magnitude 3 earthquake that happened somewhere offshore Kodiak. But it's encouraging to be able to see that, you know, they have really nice looking waveforms with some interesting features embedded in them probably here. I won't go into detail, but all the way out to, you know, many hundreds of kilometers away. And again, at full azimuthal range, which is still quite unusual for a subduction zone, kind of offshore subduction zone setting. Okay, and so finally, not only is the AACSE seismic and seafloor pressure data available on IRIS, but there is a community catalog, earthquake catalog, that is being generated that I think is going to really sort of accelerate and facilitate a lot of the research we're interested in the next few years. And so this community catalog is being coordinated by Natalia Rupert at the AEC, as well, along with Grace Sparchek and Jeff Abers. And I have a quick map of it here. You can actually download the catalog through 2018 from the IRIS site. Here's the network code, AACSE, pretty exciting. But I have this map really small on purpose so that you can't actually see it. So you'll have to tune into Grace's poster at this meeting and find out all the details, as well as some of the work she's doing to kind of beef up the catalog using machine learning tools. So I would encourage you to do that. And this is my last slide. I can't imagine I have any more time left, but you know, there's a lot of, I went really fast through these 4 studies, but there's a lot of more details being presented at this meeting, at posters and talks. So definitely look for those. And I'll just finish with a note that, you know, despite all the challenges we had in the last year, I think there's really a lot going on with regard to thinking about earthquakes and plate boundary processes at using marine seismic tools. And so there's a lot of work to do and a lot of things to look forward to. And with that, I'll say thank you again to the conveners. And if there's time for a question, I'd be happy to take one.
Yeah, and thank you so much, Emily. That was great. And you're very close to 8 on time. So, but almost. But if there's a couple quick questions, feel free to unmute yourself or raise your hand, and we get time for a couple quick questions.
Looks like Michael, do you want to go ahead?
Yeah, since nobody else is asking a question, I would like to ask, as a secondary science teacher at an international school in Thailand, are there any opportunities available for like education specialists for me on endeavors like these? I mean, I loved your presentation. I find it very intriguing and interesting. And so I would like to look at the possibility of, you know, opportunities as an educational specialist on any of these for outreach purposes.
Yeah. Well, I'm really glad you asked that question, Michael, and thank you for doing so. I'm probably not going to be able to answer it as well as some others at this meeting will be able to, and definitely check out Abrea's talk on the last day of the meeting. But I can tell you that, you know, depending on which experiment you're looking at, it's common for scientists to be looking for opportunities to connect with, you know, K through 12 educators, and it sort of depends from experiment to experiment what resources they have available to do that. But for example, on the AACSE, this last experiment I was just talking about, there was I think at least one of our cruises, and it might have been more than one of the 5 that had educators involved, and I think there were only 2, but they came to see, I think, purposefully with the goal of thinking about developing some curriculum that would, you know, use seismic data, but still be appropriate for K through 12 education. And so I can put you in touch with people who would know more details about how that evolved. But I think in some ways, connectivity is sometimes the biggest obstacle with this, is just matching up scientists with educators and making sure we have the right resources.
Absolutely. Yeah. I mean, not to take up too many times, and Sean, cut me off, please, if I'm talking too much. Yeah, I've been involved in 2008 with IRIS, you know, seismograph in schools programs and all that. And I actually have 2 seismographs in my classroom. So definitely it would be for the purpose of developing curriculum and stuff, and being here in Thailand now. And I don't perceive myself moving on anywhere else. I think I love it here in Thailand. I'm going to be staying, and my international school actually sits on a university campus. So we're actually under the umbrella of a university, which is a technology university. So definitely, you know, it would work to the advantage, you know, of it. And so I, you know, really want to broaden my horizons on this.
Great. No, I think there are opportunities, and maybe, yeah, making connections is a good goal for the very near term. So.
Thank you. I appreciate anything you have. Thank you.
Great.
All right, with that, I would encourage anybody else to put more questions you have into the chat window, and we'll try to come back to those. But thanks, Emily, so much for that. Next up, we have Dr. Donna Shillington, who unfortunately I have to say at the Northern Arizona University as an associate professor. She left about the time pandemic started, and since no one's been at Lamont, I can pretend she didn't leave. But spent much of her career at Lamont, and moving all the way from Doherty Associate Research Scientist up to a senior, Lamont Research Professor. And left Lamont in January of 2020, and now is an associate professor at Northern Arizona University in Flagstaff, Arizona. And originally came from her PhD in geophysics at the University of Wyoming. And it's my great pleasure to have Donna speak here for this meeting, along with Monica and the rest of the conveners.
Thank you so much, Sean. Right. Can everyone see my screen okay? Great. Yeah, no, thank you so much to Sean and Monica and Lindsay and the other conveners of the session for giving me the chance to contribute here at the beginning. Like Emily, I'm super excited about this meeting and the chance to hear about all the exciting science that's been happening. It's been a while since we had, I guess we were just discussing before the session started, but it's been since 2017 that we had the last OBS symposium, which is a more focused, intimate chance for us to share results. And so I think it's fabulous that we're able to do that now. And kind of in that spirit and recognizing all the exciting things that are going, I've kind of taken on a pretty unwise scope for my talk. And I wanted to try and highlight some examples of new studies and results where we're using marine seismic imaging to learn pretty fundamental things about tectonic and magmatic processes that are shaping our Earth, from continental rifting and breakup through the formation and modification of oceanic lithosphere, and then the ultimate destruction of oceanic lithosphere and a deformation and magnetism that results at subduction zones. So yeah, pretty modest set of topics to cover in 20 minutes. I'm sure I can do it. And some of the work I'll show you is from myself and my collaborators, but I'll also be showing other examples that I've taken from the literature or that people have shared with me. So thanks to those of you who have shared your unpublished work for me to highlight in this talk. And yeah, as I said, I'm going to mostly focus on seismic imaging data in this talk. And of course, the power of these data are that they're able to show us the Earth structures in ways that aren't possible with any other method. And there's kind of a whole potpourri of different imaging techniques out there that can tell us about different scales of structures and different temporal and spatial length scales of processes, from really detailed constraints on fault structure and sedimentation at shallow levels from high resolution multi-channel seismic data to lithospheric scale deformation to sublithospheric scale deformation that we can get from a variety of passive source imaging techniques. And something that I think is really exciting in recent years is that we have more and more places where we have combinations of these data plus other data like magnetotellurics and geology and other things available that we can really start to develop more comprehensive portrait of Earth structure, and from that a better understanding of processes. All right, so as I said, I'm going to try and dance through a few different themes in this talk, starting with continental breakup, magnetism and extension during continental breakup, and wanted to kind of highlight two different examples. So a common set of questions that we have for how continents rift is, how is deformation accommodated throughout the lithosphere, and when and where is magma involved within that? And that question kind of spans from the earliest stages of continental rifting through final rupture and initiation of seafloor spreading. And so for the first example I wanted to show you is from the early side of that, from the kind of first stages of continental breakup. And it's an example from the southern part of the East Africa rift. And at first, it would not seem like marine seismology is a particularly useful tool for studying a continental rift system, but several parts of this system are covered in large freshwater lakes, some of the largest in the world. And so if we want to get the full picture of what their structure and behavior is, kind of requires us to pull out some of our marine seismology techniques. And so as a part of a large project with many, international project with many PIs that involved kind of collecting seismic and MT and geodetic and geochemical data across this rift system, we undertook a quote unquote marine seismic study within Lake Malawi. We could not bring kind of special research vessels into this lake, and so we used ships of opportunity to deploy ocean bottom seismometers. So here's an example of here's the RV Indunduma, which deployed OBSs within the lake. It's a fishing vessel, and the OBSs are shown with dots here, and acquired seismic reflection and refraction data using a container ship that we outfit for this project. But and so some of these OBSs were just used for the kind of the active source experiment, but several of those are broadband stations that together with an onshore array provided crustal lithospheric, sublithospheric imaging. And so we, from this kind of combination of data, we were able to start to tackle the questions that I laid out to you, like how is deformation accommodated throughout the lithosphere? One of the questions at a shallower level is how is extension partitioned between large border faults that bound this and other parts of this this rift system, and the very dramatic escarpments along the rift lakes. How is extension partitioned between those and faults that are kind of hidden beneath the lake, so-called intrarift faults? And so this is the middle panel here is showing an example of a kind of seismic reflection data overlain on a velocity model from seismic refraction data that shows, the kind of overall thickness of sediments against this large border fault, but also numerous intrarift faults. And although they're clearly much smaller than the main border fault, some of them are really quite large. And from this work, we've been able to see that they have been significant in accommodating some of the extension. And not only are they large, they're active. And these faults offset the shallowest sediments and the lake floor, and which is consistent with seismicity results that come from the sort of onshore-offshore array from Cindy Ebinger and others. And so, yeah, these intrarift faults are also important for hazards as they're super active. At a deeper level, this kind of combination of this onshore-offshore array was actually able to image the crust and upper mantle. And one of the kind of exciting and surprising things we found was that there was more thinning of the mantle lithosphere than of the crust. And so this lower right-hand panel shows a beautiful receiver function image from Emily Hopper showing the shallowing of the LAB, which you can sort of see as this blue phase. And so we were quite surprised by this because in general, the Malawi Rift is relatively magma poor. There's a volcanic province to the north, but surface wave imaging doesn't allow for very much melt underneath the rift today. And in many places where we see this kind of pronounced preferential thinning of the lithosphere from a combination of thinning and corrosion, it's been in super magmatic rifts. And so this implies a possible role for magmatism in the past. All right, so that was kind of the early stages of rifting. And now we're going to move and talk about the later stages of rifting. And for that, I wanted to show an example from a recent, very grand study on the eastern margin of North America, the ENAM Community Seismic Experiment, which involved the acquisition of both passive and active onshore, offshore seismic data across this area. And so this margin is kind of has previously been considered a poster child for really magmatic rifting. But what the kind of new imaging results have shown us is a more complicated picture. And so on the right here are results from Anne Bissell from seismic reflection imaging on the upper panel, and a velocity model from seismic refraction data from Brandon Shuck on the lower panel. And what they see is if we start here on the left at kind of the edge of the margin, first things are looking as we might expect for a magmatic rift system. We have high velocity, lower crust, which might be indicative of mafic and rift intrusions. and seaward dipping reflections in the upper crust from subaerial magmatism during rifting. So that kind of conforms with our idea of a really magmatic rift. But as we carry on farther seaward, what Anne and Brandon show is something surprising. Instead of kind of a gradually thinning magmatic crust that, you know, settles down into normal seafloor spreading, they see a very thin, highly faulted crust with relatively high velocities that persists for 100 kilometers before you have a pretty rapid change to a thicker crust with much less faulting. And from their work, what they were able to determine is that, you know, one explanation for this change is that during the later stages of rifting, you still had continental mantle lithosphere here present below this rift, underlain by kind of modestly warm asthenosphere, and that combination of a remnant mantle lithosphere and some warm temperatures could explain this thin faulted crust, yet with these relatively high velocities indicating mafic material. So this is some really cool results that those guys have shown. And on top of this active source imaging, there was a large passive source imaging effort. And here I'm just showing some new results from Josh Russell. And this is a S-wave model across the same footprint. And hopefully you can see that the crust in the shallow part here, but that if we look in the uppermost mantle, you have notably lower velocities here beneath that highly thin faulted crust imaged by Anne and Brandon, and that you have a pretty rapid transition to much higher velocities as you go farther offshore. And so these lower velocities are consistent with there being continental lithosphere there, but they further require that you have to have added gabbroic intrusions in order to explain how low they are. So, so this kind of further adds to the picture of the more complex evolution of deformation and magmatism over this system. And finally, a really fabulous part of the ENAM experiment was the chance to have constraints on how structures are not just varying across the margin with dip lines, you know, which is a very common and sensible thing to collect, but also along the margin with strike lines. And so this is work from Colin Brandel on a refraction line along the margin. And the lower panel is showing a P-wave velocity model. And you can see these changes in both the thickness and velocity of the magmatic crust near the edge of the margin. And some of these changes in crustal structure appear to correlate with the extensions of fracture zones to the margin and could imply the early development of a magmatic segmentation within this rift system. So kind of taken together, these results from Malawi and from the Eastern North American margin are painting for us a much more complex picture of how deformation occurs throughout the lithosphere and when and where, and the distribution of magmatism in these systems. All right, so moving on to out into the oceanic lithosphere, you know, a long gap of in our understanding of the evolution of our planet has been sort of the structure and processes happening out within the oceans, but especially away from mid-ocean ridges, just out in the oceanic plate. For a long time, this was a really particular data gap, and we still have a lot to learn. But over the last years, there have been a number of passive OBS studies kind of targeting the structure of older lithosphere and to understand controls on its structure and on its evolution. And so the left panel is showing a map of the Pacific Ocean, and all the triangles are showing some different OBS arrays. And in particular, wanted to highlight a recent OBS study out in the Pacific, the Orca project, which had young and old orca. And there's a number of posters that show some new results from that. But there have also been a number of others. And here just highlighting one from the recent PyLab experiment out in the Atlantic Ocean. And these studies are starting to tell us a lot about what the structure and origin of the lithosphere-asthenosphere boundary is, deformation within the lithosphere and asthenosphere, the possible presence of fluids and magma in that system. And so I definitely encourage you to check out all these talks and posters that are happening on this. There have also been a couple of really epic active source studies out across the oceanic lithosphere, kind of showing us how it evolves away from the ridge. And so here I just wanted to highlight the CRUST project, which collected data over 70 million years of Atlantic oceanic lithosphere in the South Atlantic on this epic profile. And these data are providing new constraints on, the aging of oceanic crust. And then I wanted to highlight this study from Justin Estep, who used the patterns of faulting that were imaged in seismic reflection data on this profile to see how variations in the style of spreading and how much of it was magmatically accommodated versus tectonically accommodated over the 70 million years, and how it related to changes in spreading rate. So kind of a window into sort of temporal changes in magmatic and tectonic processes that we really didn't have before. And so of course the oceanic lithosphere, a huge thing that's important about it is how it is, first formed and evolves. And one of the ways in which it evolves is being modified by later off-axis magmatism. So this is just a map showing one estimate of seamounts from around the oceans. And it kind of confirms the feeling you have from looking at a map, that it's kind of hard to find a normal piece of oceanic lithosphere that hasn't been impacted by some of these other processes. And one of the most kind of epic sets of seamount chains in the ocean is the Hawaii Emperor seamount chain. But despite how common these seamounts are, and how prominent some of these chains are, such as these hotspot derived chains, we actually have very few constraints on their structure at depth and the total amount of magmatism which has been added to the lithosphere, and the response of the lithosphere to the load of that magmatism through flexure. And so in 2018 and 19, my colleagues and I collected some data around the Hawaii part of the chain and the Emperor part of the chain to try and fill some of those gaps in this very famous seamount chain. And so the panels here on the right are showing seismic reflection and refraction data collected across the Hawaii part of the chain near Oahu. And from this velocity model from Rob Dunn, you can see the flexing oceanic lithosphere here, but also that you have this very narrow, high velocity core beneath these beneath the islands, showing a highly localized zone of intrusion below that area. And then some of the kind of total width of the Hawaii seamount chain here is actually from slumping off of this core area of magmatic intrusion, and with these very dramatic and high volume features from kind of slow and fast slumping away from the islands. We can also see sort of the shape of the oceanic lithosphere as it flexes under this load, which is gives us another insight into its rheology. And one of the kind of design goals of collecting data in these two places was actually to see how that flexure changed as a function of the age of the plate. So out here in the Emperors, the seamounts were emplaced over 60 million years ago, and the lithosphere was quite a lot younger, compared with Hawaii, where you've had very recent emplacement of magmatism on a 90 million year old plate. And so this is just a comparison of from Brian Boston's work of reflection data across the Emperors in the upper panel and across Hawaii in the lower panel. And you can see quite different pronounced shape of flexure of the top of the oceanic plate between a volcanic edifice emplaced on relatively young oceanic lithosphere compared to relatively old lithosphere. So that's definitely a continued thing that we're trying to exploit from these data. And finally, up in the Emperors, a very nice thing is that there's not all these like pesky islands. So you can actually drive along and collect data along the chain, not just across it. And so with the along strike profile we were able to collect there kind of confirms what we were seeing from the dip lines, and that you have these highly localized areas of high velocity material sort of beneath these islands. All right, and so finally wanted to move into subduction zones, and here there are a number of questions that seismic imaging is required to address. Of course, we want to know the incoming plate brings water into the system, which drives magmatism at island arcs and is an important control on overall mantle rheology. We have changes in deformation along the megathrust that we would like to understand from imaging and understand what properties are associated with that, as Emily was describing, and more. And these are all things for which seismic imaging can help us with. And there've been a number of exciting studies, and I'll just highlight a few, starting out here at the outer rise. And so we've known for almost 20 years that that you have normal faults that may penetrate down into the upper mantle and cause and be pathways for fluids down and hydration of the crust and upper mantle. And a lot of our constraints over the years have come from isotropic P-wave velocity models from active source seismic data. But there have been a number of new studies that have really expanded and improved on what we could learn from those kind of studies. In the upper left-hand corner here, these are some results from Marianas, where Kai et al. And others were able to use surface wave imaging to get constraints on shear wave velocity to much greater depths than is generally possible from active source data. And their results suggest that you might have a modification of the upper mantle to depths of 20 kilometers beneath the slab, so to really large depths. Kind of in contrast, recent results from Costa Rica suggest that in that subduction zone, you might have more limited hydration below the moho. And they were able to use an active source seismic experiment to determine variations in anisotropy with depth. And between the kind of 1 to 5 kilometers below the moho and 1 kilometer below the moho, they see kind of the erasure of the anisotropy formed at the mid-ocean ridge, suggesting that that's the kind of depth range over which you have really profound and wider zones of hydration. And so that's another important constraint. And finally, in many subduction zones, focuses on the discussion of outer rise hydration is really how to focus on the uppermost mantle. But the crust is another super important potential reservoir of water that's being carried into the earth. And so this is showing an example from Tanner Acquisto's work of higher resolution constraints on upper crustal velocities using tomography of streamer data. And Tanner and his colleagues were able to see this reduction in crustal velocities approaching the trench from a combination of maybe faulting and hydrous minerals. So these are just examples of kind of relatively new things in our repertoire for constraining hydration in the incoming plate. If we kind of walk into the subduction zone, and of course another big question is what controls properties along the megathrust itself. And on the left, I wanted to show this example from a couple recent papers from new data collected on the Chilean subduction zone, the south central Chilean subduction zone, where they use seismic reflection data to image this really thick package of sediment, like over 1 kilometer, that's subducting at this margin. And based on the velocities and properties of the sediment, it looks like it's relatively well drained and strong. It doesn't have the elevated pore fluid pressures in general that are observed in many other places, and also doesn't look particularly internally deformed. And so, Olsen and Bangs and all of their collaborators have kind of used this to infer that, this broad zone of subducted sediment might be really important for creating a relatively homogeneous and strong asperity at depth. And in many other subduction zones, increasing availability of seismic imaging has been able to show us changes in the properties of what's subducting and what the plate boundary properties look like that might be related to changes in behavior. And so here I just show an example from along the Alaska Peninsula, where we saw changes in the thickness of sediment subducting between 2 places that are behaving really quite differently. Another kind of higher resolution target for this important subduction zones are volcanoes and their plumbing. And I just wanted to show this fabulous example from Santorini of a really epic volcano imaging study, where they were able to do detailed 3D imaging of the upper crust below Santorini and map out low velocity zones, and thus to constrain the distribution of a shallow magma chamber and how it might be controlled by faulting and the kind of shape of the edifice and the load of that at a higher level. And I'm getting close to the end, I promise, if I'm running out of time here. But another kind of important question in subduction zones is just what is the overall composition and thickness of our crust, and what controls its variations. And for, now 15 years ago, there was these fabulous set of results have come from the Izu Bone and Mariana subduction zone that show us changes in the thickness and velocity structure of crust that correlate with the composition of volcanoes at the surface. And we haven't had very many points of comparison to this. And so I was very fortunate in the last year to, despite COVID, have a chance to go to sea on a project led by Dan Lizaraldi and collect some active source seismic refraction data along and across the Aleutian Arc to understand how in this subduction zone crustal structure changes. And it would be an interesting comparison to Izu Bone. And finally, I'm going to end with just highlighting the AACSE experiment, which Emily already described, but the availability of these more epic passive source imaging experiments like this, and off of Cascadia and elsewhere, like providing a view of subduction zone structure that at a scale that hasn't been possible before. And so it's going to be so exciting to put this together with what we've seen from previous studies here and elsewhere. And so with that, I'll conclude. There was like a few too many things there to have a real sensible conclusion, except to say that marine seismic data are showing us so many basic and fundamental things about how our planet is working and continue to bring us new surprises. And so, yeah, I'm excited to see what everyone's been up to and by watching all the talks and posters over the coming couple weeks. And just wanted to end by a big thanks to the people that make the acquisition of these data possible, the people who run our marine facilities, our research vessels, our OBS facilities and other facilities. These people we couldn't collect the data without them. They're totally instrumental to everything that we're doing. And the availability of these kinds of facilities has really democratized the ability to get out in the oceans and collect data in a way that's just fabulous. So thanks to all the people who are doing that, especially at this time when it's become even more complicated to get out and collect data and involve greater hardship for the people involved with longer time away during quarantines prior to going to sea. So yeah, big thank you to all of those people. And of course, a thank you to the agencies that fund the science. So with that, I will end. Thank you.
Thank you so much, Donna. Your tour of all the Langseth cruises is painful in some ways, but it's still great to see them all.
Oh.
We've got some time for a question here. So if anyone would like to unmute themselves and ask a question before we move on to the last segment of the session this evening.
I have a question regarding the lithospherical thinning beneath the rift zone, especially beneath Malawi rift that you showed. Oh, by the way, your presentation is awesome. I love the data that you were showing. It's beautiful. So the thinning of the lithosphere beneath rift zones, is it like still under debate, or is there any ambiguity of the thickness of the lithosphere based on, for example, S2P or P2S conversion?
So at least so for the Malawi rift, it feels like the different data sets we have are all showing us a consistent picture, both the S2P, so the image I showed was an S2P receiver function image, and the surface wave imaging, they're all showing a consistent picture. And in fact, there are other authors who've estimated lithospheric thinning from gravity data, and they also infer sort of preferential thinning of the lithosphere there. I think what's interesting in the two examples I showed is that they have the opposite sense of crustal versus lithospheric thinning. So I think it tells us that in general for rifts, we still have a lot to understand about how that works. In the Malawi rift and in this relatively early stage Potpourri rift, we see preferential thinning of the lithosphere compared to the crust, whereas off the eastern margin of North America, what Brandon and Anne and Josh's and others results have shown us is that it looks like you had leftover lithosphere compared with the crust. And so I think the now that we see, we see in even more detail in more places these depth varying ways in which the lithosphere is deforming, shows us we have a lot to learn. So I don't know if that quite answers your question, but I would encourage you, there's gonna be a talk tomorrow from Jim Garrity that's on more detail of that Malawi rift experiment. So
That's
yeah,
great. I'm looking forward to it. Thank you so much. Thanks.
Thank you.
All right, with that, I would thank Emily and Donna again for great talks this evening. It was a great way to start off the symposium. Behalf of everyone, Monica and myself and all the conveners, thanks again for this. It was really great. And I will turn things back over to Casey.
Okay, thank you. I'm just going to post some of those links that I didn't quite get to you guys earlier in the session. And I think, Lindsay, you're available for, I can just get this. Okay, now you can see a slide.
Yes.
Lindsay, you there?
Yes, I'm here. Hi.
Okay, sorry. Great.
Hi, everyone. We just wanted to take a second to highlight to all the attendees our special interest group session on justice, equity, diversity, and inclusion. That will be on Wednesday. So I think Emily and Donna just took us through amazing advances in our technological and analytical capabilities. But as we all know, there's been very little progress on diversity in the geosciences in the last 40 years. And so the idea for the session is just to provide a space for discussion and collaboration on action-based strategies to address racism and exclusionary issues in the geosciences and marine seismology specifically. So we're hoping that the SIG will serve as an opportunity to make connections and share ideas, ideas for best practices, other ongoing efforts at your home institutions. Whether you've been working in the DEI space for many years or whether you're new to it, we welcome your contributions. This work is for everyone, and so we hope to see you there. Thank you very much.
Great, thank you. And you can still hear me, correct? I think I muted myself. Okay. And I'm just going to close it out now, but before I do that, I do want to reiterate a few points that were made. And I know we are all really excited for the science being covered over the next 2 weeks through both the live and recorded sessions, the poster areas with pre-recorded videos, slides, and posters, and the presentations, tutorials, and discussions that are going to be happening in those special interest group meetings, including the one that Lindsay just invited everyone to. This is an ambitious agenda with sessions covering some of the most cutting-edge research from around the globe, and we hope that you enjoy this symposium as much as one of our previous in-person meetings that we've held in Redondo Beach in California, Vancouver, Washington, and most recently in 2017 in Portland, Maine. And also on this International Women's Day, we want to celebrate the significant work, contributions, and representation of women in this symposium program, and more broadly in marine seismology. I would like to take a minute though to recognize those who are not here and who will not be joining us for this symposium. The geosciences are the least diverse of all STEM fields in the United States, and there has been no progress on this in the past 40 years, as demonstrated in the Bernard and Cooper Doc 2018 paper published in Nature Geoscience. If we are to make progress on the ethnic and racial diversity in our community, as we have done with the representation of white women in the geosciences, we need to go beyond recruitment and focus on changing the culture of our field to improve retention. We must address this through a commitment to anti-racism actions, training in bystander intervention, actively questioning the unwritten rules and norms of our field, and using or seeding the power and platforms we have to enable Black, Brown, Indigenous, Asian, Pacific Islander, Middle Eastern, and North African, and other people of color to be safe and thrive in our community. If you have not already done so, please read and sign the 2 calls that were sent out to our community. A call to action for an anti-racist science community from geoscientists of color, Listen, Act, Lead, and call for a robust anti-racism plan for the geosciences. You can also tune into the Unlearning Racism in Geoscience, or URGE, interviews and curriculum that are currently underway. On behalf of myself myself and the Marine Seismology Symposium Organizing Committee and team, we hope you will all participate fully, engage in discussions, and welcome new members of our community. Please review the IRIS Meeting Code of Conduct, adhere to those standards, and ensure our community is a safe and welcoming place for all to share ideas and exchange experiences. Thank you again to Sean and Monica for convening this first session of the Marine Seismology Symposium. And thank you, Donna and Emily, for your excellent presentations. Thank you also to Jinhua, Liam, and Masako, and the many great panelists in their early career session. Recordings from both sessions will be posted on the symposium website under the event pages within 24 hours. Thank you to all of the Symposium Organizing Committee members, Emily Roland, Masako Tominaga, Anne Trehu, Bob Woodward, Patrick Hart, Donna Shillington, Sean Higgins, Sean Gulick, Monica Kohler, Helen Yaniszewski, Lindsay Worthington, Anne Bissell, John Orkett, Guillermo de Melo, Jinhua Gong, Liam Moser, whom you will all see as conveners and speakers. And thank you to team members Kristen Poitra and Molly Statz, who keep the gears turning and made this planning process fun and not as overwhelming. We appreciate everyone's patience as we navigate these virtual meeting waters and welcome your feedback. Please do get in touch with any questions or comments. Reach out to a member of the organizing committee, connect with those student attendees, follow up with one of the speakers, and we look forward to seeing you during the rest of the symposium. Thank you.